minus 1.6 times 10 to the minus 19 coulombs. This number, you have to memorize this. Charge, unit charge is 1.6 times 10 to the minus 19 coulombs. So proton, we call it 양성자, proton. The mass of proton is 1.6 times 10 to the minus 27 kilogram. And charge, this time is plus 1.6 times 10 to the minus 19 coulombs. Neutron, 중성자, 1.67 times 10 to the minus 27 kilogram. So the mass of proton and neutron is quite similar. A neutron is a little bit heavier than proton, but it is quite similar. But compared to the proton, electron mass is quite small. It is about 2,000 times, 1,800 times smaller than proton mass. Okay, electric charge of neutron is neutral. Times 10 to the 8 meter per sec. Okay, you have to memorize this number. So from this slide, you don't have to memorize the mass of electron, proton, and neutron, but you have to remember the mass of proton and neutron is quite small, quite similar, but electron mass is quite smaller than smaller than proton and neutron. And you have to memorize the electric charge unit, 1.6 times 10 to the minus 19. And you have to memorize the speed of light. Now, this is a notation for atom. So X is like copper, Cu. So this is notation for the atom. And Z means number of proton, and N means number of neutron, and A means mass. So A equals Z plus N. So Z is a number of proton, A is mass number. Okay, X is X is element nomenclature. Normally, we don't we omit N. We just write Z and A only. So this is basic notation for an atom. And in the table, you can see isotopes. Isotope, 동위원소. Isotope means equal proton number. So carbon 12 or carbon 13 is isotope, 동위. In Korean, 동위 means same place. Same place in periodic table. 주기율표에서 같은 자리에 있는 게 동위원소입니다. So isotope means equal proton number. So the sequence of periodic table is given by number of proton. So that means C12 and C13 is in the same place. That means 동위, 같은 위치. So we call it isotope. Isotone means equal neutron number. So C13, we have proton number 6 and neutron number 7, okay? And nitrogen 14, proton number 7 and neutron number is again 7. So these two elements have the same neutron number. So we call it isotone. And isobar means equal mass number. So even nitrogen, oxygen, and fluoride, all the mass number is 17. So this is we call isobar. And mirror, mirror means a mirror. Neutron and proton number are exchanged. So in tritium, we have one proton and two neutron. So in helium-3, we have two proton and one neutron. This is mirror. A nuclear isomer. This technetium 43 and 99. Again, technetium 4399, M means metastable. So this is the same element and same number of proton and same number of neutron, but the stability is different energy state. We call it isomer. So you have to memorize this table. And atom and molecular weight. Uh, we already saw the weight of atom or weight of proton and weight of neutron is too small to be measured by kilogram. 10 to the minus 27, 10 to the minus 31. It is quite small number. So that means measure the measurement of atomic and molecular weight by kilogram is too large unit. So we need smaller unit. So we defined the lower part AMU, atomic mass unit. So we defined we used carbon 12 as a reference. So uh, the mass of one carbon 12 atom divided by 12 is we call atomic mass unit. Okay, atomic mass unit. And we know the Avogadro number. So we have, if we have Avogadro number 6.02 10 to the 23. So if we have carbon 12 atoms of Avogadro number, we got it 12 gram. Okay, so that was the definition. Okay. So this example is for the isotope abundance. So this is a oxygen isotope. So we have oxygen 16 and oxygen 17 and oxygen 18. The natural abundance is mostly 99% of is oxygen 16 and 0.037 is oxygen 17. 0.204 is oxygen 18. So it is the abundance. So in the parentheses, we have not A slash O. This is atomic percent, not just percent. So this we have atomic percent. And the actually atomic weight of oxygen 16, 17, and 18 is given. So in order to um, get an average atomic weight, we have to multiply the first line and second line and third line and add up like below, and we get 15.99938. So this is uh, the atomic weight of oxygen. Okay, so when we get this number, we accounted the abundance of an isotope as well. Now, atomic and nuclear radii. Uh, the complex form of radius is radii, right? So this radius 1.25 femtometer multiplied by cube of A, one third of A. So this is the radius of atom. You know, an atom is composed of one nucleus and electron orbits around the nucleus, right? So when we measure the radius of atom, that means the radius of electron orbit, outermost electron orbit. So mostly the radius of atom is 10 to the minus 10, 10 to the minus 10 meter. But 10 to the but the radius of nucleus is 10 to the minus 15. So 5-digit difference. Okay. So actually, when we saw a figure showing nucleus and surrounding electron orbit, so actually the size of nucleus is quite small compared to the size of atom. So that means the figures you are accustomed is quite exaggerated. So actually, the size of nucleus is very, very small compared to the size of atom. So now, mass and energy. So Einstein's theory of relativity, 상대성 이론, Einstein's theory of relativity tells us that mass and energy is equivalent and convertible. So the formula is rest energy over mass is mc square. Okay. So c, you know the speed of light. Okay. So when we measure the atomic and molecular energy, joule is a so big number. As I told you, when we measure the mass of an atom, kilogram is a too big unit. So we need smaller unit. So we defined atomic mass unit, right? So like the same way, when we measure the energy of atom or energy of electron or energy of neutron, we use electron volt. So unit charge is 1.6 times 10 to the minus 19. You already memorized that. So actually that is a coulomb. Coulomb per second means ampere, right? So coulomb times 1 volt, that is 1 electron volt. So 1.6 times 10 to the minus 19 joule is 1 electron volt. So in nuclear engineering, we use electron volt more for the measurement of atomic level of energy. So this is an example. So the rest mass of an electron, we have the mass of electron is 9.1 and 10 to the minus 28 times speed of light. So this is not SI unit, this is CGS, centimeter. So 10 to the minus 28 and 10 to the 10, that is centimeter, right? So we got it, we get the calculation, and 8.1 times 10 to the minus 14 joule. So this is even the nuclear energy. So the energy is quite smaller than 1 joule, 10 to the minus 14. So when we express this energy in mega electron volts, it is 0.511 mega electron volt, MeV, we call it MeV. So this is the rest mass of electron. So when the electron is disappeared and the energy is released, then we get 0.511 MeV. Okay? So sometimes we use this in hospital. So when we get cancer diagnostics, so we use positron emission tomography. Positron. So positron is electron but have positive charge. So the same property with electron but have a positive charge, not negative charge. So there is an element that emits positron when they irradiate radiation. So when the positron appear, it combined with electron nearby, and it just combined and disappear, and 0.511 times 2, because two element, so positron and electron. So 1.022 MeV radiation appears. So when we measure the radiation, we can fix the location of positron. So you have to memorize this number, 0.511 MeV. That is the rest mass energy of an electron. Okay? Now, kinetic energies. So we have three different formula. The first one, when the kinetic energy is less than 0.02 rest mass, the kinetic energy is 1 over 2 mv square. That is just classical definition of kinetic energy. So that means for the very slow speed particle, we use just classical definition of kinetic energy, half mv square. But if the energy of particle is higher than 0.02 rest mass energy, so that means it moves fast, then we use equation uh, uh, for relativity. So kinetic energy becomes mc square and the bracket. So we call it this bracket. This is the kinetic energy for very high speed particle. Okay, and for the photons, the rest mass of photon is 0, but it has kinetic energy. So in the above two formula, if the rest mass m0 is 0, then kinetic energy should be 0. But actually, there is a kinetic energy of a photon, even though the rest mass is 0. So we need another definition of kinetic energy. So E equal h nu. The h is Planck constant and nu is frequency. This is not v, this is nu. So this is the kinetic energy of photon. Now, particle wavelength. If a particle is moving with the speed or with the momentum, then we can calculate theoretically the wavelength of the particle. So lambda is the wavelength equals Planck constant h divided by p, momentum. So for non-relativistic case, momentum can be expressed like this. First line, square root 2me. So we put the definition of P to left hand side. So then the wavelength lambda equals square root 2m0e over h. Okay, h over square root 2m0e. Sorry. And for the relativistic case, the that is energy of a particle is higher than the rest energy of 0.02 rest energy. So in that case, the momentum is given like this. You have to uh, memorize it for that for a while, and then put this into the equation, and we get this one. And for the photon, the momentum is E divided by C. So we put this expression for momentum to the de Broglie wavelength formula. Then we get lambda equals hc over E. So the non-relativistic momentum, you can calculate this from the definition of kinetic energy. E equals 1 over 2 m0 v square. You can calculate the momentum. If you can't, you have to do that. You have to learn. For the relativistic case, I just told you, you have to memorize this for a while. You will learn atomic physics during your second year. So in the atomic physics, you will learn why we have to calculate the momentum of a relativistic particle like this. Uh, in this lecture, I will not cover. I will not. I don't have time to cover this. So I will ask you just memorize this and learn from atomic physics course. Now, this is the excited state of an element. So, this is hydrogen. So in the hydrogen, we have a hydrogen nucleus inside, and then we have a orbit. So there is a fundamental orbit and next level orbit, the next level orbit. So when electron exists in the lowest orbit, we call it ground state, 기저 상태, ground state. So when the electron stays at the innermost orbit, we call it 기저 상태, ground state. And when we gave energy to the electron, and the electron moves to the next level of orbit, higher level of orbit, we call it excited state. Okay, excited state. So there is a certain discrete orbit. That means, look at this. In this we have orbital energy of 10.19, and we have 12.07. So when the electron stays in the 12.07, and when the electron falls to 10.19, we have extra energy of 1.98. So when the electron from the high orbit, 12.07, fall down to 10.19, the extra energy is emitted in the form of gamma ray. So if X-ray and the gamma ray actually is the same, X-ray has smaller energy, gamma ray has larger energy. But these two, X-ray or gamma ray, are all photon. The same property. The only difference is the energy. So if we have the photon has small energy, we call it X-ray. If the photon have high energy, we call it gamma ray. So uh, in the high school chemistry course, we learn there is an orbit around the atom, and there is excited state and ground state. And sometimes we call it K shell or L shell. And this is the uh, energy state of an electron. Now, we model the same kind of energy state exists in nucleus as well. Okay, so inside of nucleus, we have a similar structure of energy level. So there is a discrete energy level. Discrete is discrete 뚝뚝 떨어지는 거야. 계속 continuous 아니고 뚝뚝 떨어진 discrete energy level inside of nucleus. So when the nucleus is in the ground state, the energy is quite small. But if it has higher energy, then we call it excited state. And when the excited state become ground state, the difference between the orbit and orbital energy comes out in the form of radiation. That means radiation, 방사선, radiation radiation is emitted from a nucleus during the stabilizing process. 안정화되면서 그 차이에 해당되는 에너지가 방사선으로 나온다는 거야. 그러니까 안정하지 않은 핵이 안정한 상태로 내려오면서 그 차이에 해당되는 에너지가 뭐 감마선 이런 걸로 방사선으로 나오는 거지. 만약에 그 에너지가 크면은 감마선으로 나오는 게 아니고 어떤 파티클로 나올 수도 있지만. Okay. So we assume the similar structure of electron orbit is a nucleus orbit. So there is a discrete energy state of nuclear particle inside of the nucleus, and when the unstable atom becomes stable, it emits radiation for the difference of energy. Now, this is a very important graph. When we see the graph, what we have to see first? Name. Chart of nuclide showing stable and unstable nuclei. So this is the name of this graph. If we don't look at the name of the graph, it is just the fine art. And second thing we have to see is the axis. The horizontal axis is neutron number, and vertical axis is proton number. So number of neutron and number of proton. So when we see the graph, first, name of the graph. Second, axis of graph is important. Okay. Third, you have to bear in mind that graph is given because graph is more efficient to deliver message than text. When we study, if we have graph or figure or table, we tend to think we don't have to read large text because the graph and figure and table take large area in the textbook. But actually, we have to look at the figure because it contains a lot of information, more information than text. Okay, anyway, so this is the figure for the element. So what we have to focus is from the small one, from small particle. small proton number and small neutron number. The ratio of number of proton and neutron is 1 to 1 normally, okay? 1 to 1. But this area, if the nucleus become heavy, it tends to have more neutron than proton, okay? More neutron than proton. And we assume neutron inside of the nucleus. Neutron acts like a glue, 접착제. So inside of small space of nucleus, we have several protons. Then protons have the same positive charge and very, very strong repulsive force, 반발력, repulsive force, because their electron charge is not very much, but they are too close. They are so close because the size of nucleus is quite small. So when there are more than several protons in nucleus, they will experience very strong repulsive force, but they are staying within nucleus. That means something just attached to them and glue them to become within the nucleus. So we believe neutron inside of the nucleus act like a glue that attach protons. So in the heavier nuclide, there are more neutron than proton, right? So this graph shows more neutron. We call it neutron rich. So in the smaller light element, the number of proton and the number of neutron is quite equal, 1 to 1. But for the heavier particle, the number of neutron is larger than number of proton. That means when there is a nuclear fission, there are more than 2 fragments of uranium-235. We call it fission product, and that fission product is quite neutron rich. So it has to emit electron to become stable. So in this slide, for the neutron-rich element like O19, they emit beta minus. That means electron beta minus and become fluoride 19, so that they become stable. And if neutron is lacking, positive electron, that means positron, is emitted, and this way they become stable. So this graph is quite important graph, because when the nucleus become heavier, then we need more neutron. Now, when we call radiation, we call the radiation is alpha ray or beta ray or gamma or neutron. So the 4 different types of neutron radiation we experience, and the alpha ray start first. Alpha ray is actually the helium particle is alpha. So helium is 2 proton and 2 neutron element is helium. So from 92 to 38 uranium, that means number of proton is 92 and number of proton and number of neutron is 238. And it emits alpha. That means subtract 2 from 92 and subtract 4 from 238. Then it becomes 90 and 234. The element which has 90 proton number is thorium. So this line shows when uranium-238 emits alpha, it becomes thorium 234. So that is alpha. When any element undergoes alpha decay, the number of proton reduced by 2, and the number of atom mass number reduced 4. That is alpha ray decay. And when we call beta minus decay, mostly beta minus decay, when the beta minus decay means an element emits electron. So that means the neutron become proton after emit electron. So when an element undergoes beta decay, neutron is changed to proton. That means number of proton increased 1 and number of neutron reduced 1. Okay? When there is a beta plus decay, that means positron is emitted from the nucleus. Then the proton become neutron. That means the number of proton reduced 1 and number of neutron increased 1. And electron capture is the right hand side figure, and the nucleus captures innermost orbital electron. That means the electron is absorbed in the nucleus, and then it is merged with proton and become neutron. So when the electron capture happen, number of proton reduced by 1 and number of neutron increased by 1. Okay? Now, figure 2.6. So this figure shows how cobalt-60 is decayed into nickel-60. Cobalt-60 is the radioactive material frequently used for non-destructive testing. So it is like chest X-ray we experience in the hospital. So there is a film, and the other side of our body we have an X-ray emitter, and the X-ray penetrate to our body and get an image on the film. So the same way, material. One side of material we have cobalt-60 source, and the other side of material we have film. So when the cobalt emits a very strong gamma ray, it penetrates to the material and leave an image on the film. So in that way, we checked whether there is a crack inside of the material or not. So anyway, cobalt is the most popular element we use for the non-destructive testing. We call NDT, non-destructive testing, 비파괴 검사. So cobalt-60 becomes nickel-60, not strictly. So it has to emit beta to become nickel-60. But nickel-60 has 4 different states. So below there is a ground state 0.0. Above that we have 1.332. Above that 2.158. Above that 2.506. So there is a 4 different energy state of nickel-60. So this figure shows almost 99% of cobalt-60 decays into 2.506 energy state of nickel 60, and it emits first arrow, this one, to go to 1.332 energy level. There is one gamma, and from 1.332, in order to become zero ground state nickel 60, it emits another gamma. But some element goes directly to beta decays to 2.158, and it directly go to ground state. Okay, so a very small one, 0.24% of cobalt 60 goes to 1.332 energy state of nickel 60, and it emits energy to become ground state of nickel 60. So this is quite a complex pattern of cobalt 60. So it is a probability. The decay is a probability. So some decays into 2.506 energy state of nickel 60. Some goes to 1.332 energy state of nickel 60. So for all the radioactive material, we can draw the same kind of drawing, like figure 2.6. So for the expert, they have a small booklet of element decay table. So now let's call it a day. This is the end of my slide prepared for you to this lecture. Okay, thank you very much. Bye bye. Hello everyone.
네, 오늘 수업은 마치겠습니다. 수고하셨습니다.